So you will get one compound here. And to get the, for example, you want 100 compounds here, right? So 100 compounds, you need 100 compounds. So what you do, you need to keep the 100 reactions. Okay. So to get the 100 compounds, you need to keep the 100 reactions here. So from each reaction, you will get one compound, right? So it is a time-taking process, right? And it is very expensive process also, because you need to use chemicals. There is a wastage of chemicals here. You need to use more number of solvents also here. Okay, so it is a time-taking process and waste of chemicals and very expensive process, right? But if you follow this combinatorial synthesis, right? So instead of keeping 100 reactions, you will keep one reaction, you will get the 100 compounds, right? From one reaction here, from one reaction, okay, one reaction here. So it gives, it is 50 or 100 products, okay? It gives 100 products here. So it is in a short period, right? So in a short period, and by keeping less reactions, right? So not exactly one reaction. So within one or two reactions, right, you will get the 100 products here. Okay. So what is the helpful here? So it is time reducing process. Okay. So the conventional method where it is time taking process here, time consuming process, but this method is, it reduces the time taking for the reaction, and you will get a large number of compounds, right? Yes. Yeah. Is it audible?
Yes, sir.
Yeah. Okay. Fine. Okay. So in a short period, you will get the large number of compounds, right? We call this is the chemical libraries, other synthetic libraries, means the compounds which are produced by the combinatorial synthesis is called the synthetic libraries here. So how we are getting this particular large number of, you can see with this example here. And this particular method, right, combinatorial synthesis method is applicable in peptide synthesis, right? In means most probably you will use this method in the peptide synthesis and some heterocyclic compost production here, right? So in these two fields, it is frequently used method here, right? So and the starting materials, right, is called the building blocks in this particular combinatorial synthesis. The starting materials which are used to get the products is called the building blocks here, right? So you can see here where we are taking, this is the hypothetical, right? So three set of compounds are taken, right? Three set of compounds are taken here. And here, these are the building blocks here, means the starting material, right? So you see the set of three compounds here, the A1, right, A2, and A3, right? So we are taking in the first set, there are three compounds are taken, A1, A2, A3, three types of, three set of building blocks here. And in the second one, where we are getting, where we are taking B1, okay, B2, B3. These are another three kinds of building blocks. And in the third set, where we are using the C type, C1, C2, C3, right? So total, how many building blocks we are taken? There are 9 building blocks are taken here, right? 9 building blocks are taken. And from each block, we are getting 9 compounds, right? From A type of building block, we are getting 9 compounds. From B type of building block, we are getting 9 compounds. And from, right, so A3 type of building block, we are getting 9 compounds. So total, it is 27. Okay. So from 3 types of building blocks, we are getting the 27 products here. 27 products by using only 3. Okay. So 3 gives the 27 products here. So like that means what, so here, what is the advantage of this method here? So instead of keeping the 27 reactions, right? Instead of putting the 27 reactions, simply you can right, you can keep the 3 reactions and you will get the 27 products here, right? So you can see here from A kind of, right? So from A set of product. So when it is combined with the B type, okay, so it becomes A1 B1, right? And that one further it is combined with the C type of building block here, then it becomes A1 B1 C1, and A1 to the A1 B1, where you add the C2, then it becomes A1 B1 C2. And when you add the C3, A1 B1 C3. Okay, so same, right? So same thing is repeated here. Then after that, to add the, right, C1 C2 C3 to the A1 B2 here. Okay, so like that. So A1 B2 C1 here, then you add the, right, so C2 to this particular A1 B2, then A1 B2 C3, sorry, C2, then you add the C3 to this A1 B2, then it becomes A1 B2 C3, right? Next here, right, you take this particular A1 B3, right? Here is a A1 B1, here is a A1 B2, here is a A1 B3. Okay, so A1 B3 here. Same C type of building blocks are added to this particular dipeptide here. A1 B1, it is dipeptide, and further we are going to produce the tripeptide, for example. Okay, so we are going to produce the tripeptide. Then what you do, you add the C type of building blocks, right? And you again you perform same reactions. Okay, means here all these dipeptides are present in the, right, in a particular vessel here, right? So in this particular vessel, okay, so here the A1 is there. To this A1 we are adding the B1, then it becomes, right, A1 B1, right? So to this we are adding C1, for example, then it becomes A1 B1 C1, right? So like that. Again, to this A1 B2, okay, to the A1 B2, add the same C1, C2, C3 here. Then from this we are getting 3 tripeptides here. And for this, right, A1 B3, you add the C1, C2, C3. Then it becomes A1 B2 C1, then A1 B3 C2 here, and A1 B3 C3. Right. So from this we are getting 3 tripeptides. From here we are getting three. So, right, from here we are getting 3 tripeptides. From here we are getting 3 tripeptides, right? So with A1 building block we are getting total, how much is it? 336, okay, and 9. So 9 tripeptides are getting. Now again you take, right, so here we are taking A1. Now you take A2 here, okay, to A2. So to A2 you add B1 here. Then what you, so what you get here? A2 B1, okay, A2 B1. Now we add, okay, B2 here. Then it becomes A2 B2. Now you add, okay, B3.
A3 B3.
A2 B3 here. So we are getting 1, 2, 3, 3 dipeptides here. Okay. So to this A2 B1, again you add C1. Then it becomes A2 B1 C1.
C1.
Right? And to this A2 B2, we add C2 here. Right?
A2
We add C2. Then it becomes A2 B2 C2.
C2.
Okay. And to this A2 B1 B3, you add C3. Then E2 A2 B3 C3. So all are different, right? We are getting different products here. Okay. So this is the method to produce the different types of products in a single reaction. So all these are, okay, all these products are obtaining in the single reaction. Okay, we are not going to keep the means here how many compounds we are getting. From this we are 9 compound. From A2 we are getting 9 compound here. From A3 also same. 9 compounds. So total 27 compounds, right? 9 plus 9, 18 plus 9, 27 compounds. So to get the 27 compound, right? So we are putting only one reaction. So from one reaction, we are getting the 27 products here. So it is a very economic reaction, right? This combinatorial method is a economic method here because when we are saving that it's time saving process here, and you can what is it? You can save the money also here, and where the reagents, solvents, all the chemicals are saved in this particular method. So this is the major advantage of this particular combinatorial synthesis, right? And this particular combinatorial synthesis is not suitable for all kind of reactions. Only few, right? Only few types of reactions. Only few fields are suitable for this combinatorial synthesis, and it is frequently used in the peptide synthesis. Okay, you know that peptide synthesis. Peptide means where polypeptides. Okay, where the amino acids combines and it gives a dipeptide, tripeptide, pentapeptide, polypeptide, like protein synthesis. Okay, so in that method, it is very useful method here. And in the synthesis of heterocyclic compound in the drug chemistry, right? Because in right, so in nature, okay, there are 80%, okay, 80% of drugs are heterocyclic only, right? So most of the drugs are heterocyclic only. So in the drug chemistry, this combinatorial method is applied here. Okay, right. Next, differences. Okay. So, and generally, this combinatorial synthesis is right suitable for this in the solid phase, right? Medium, right? In the solid medium here. So, what are the differences for this solid medium and the solution medium, right? So, most of the reactions, right? Most of the 95% of the 95% of the reactions are carried out in the solution phase, right? In solution phase here. And the solution phase is very convenient method. All the reactions, what you are the reactions you will keep in the lab, right? So already in your first year, you are done the synthesis preparations, okay? Preparation of benzene. You prepared the para bromoacetylide. You prepare the hippuric acid, right? So all these reactions. So you are followed the, okay. So you are followed the means you done in the solution phase. You are not used the solid phase here. Okay. So to perform in the solid phase, you need to, right? You need to apply some requirements here, right? And the merits and demerits of these two phase reactions, like solid phase reactions and the solution phase reaction. So what are the advantage in the solid phase synthesis, and what is the advantage in the disadvantage in the solution phase synthesis, right? So in the solid support reactions or the solid phase reactions, right? So generally, okay, so this particular solid phase reactions, right? So it can be, it is easy to perform here, right? The solid phase reactions are very easy to perform, okay? And the solution phase reactions, it is somewhat difficult when you compare with the solid phase here. Okay, because in the solution phase, there are so many purification methods are involved here. Okay, so in this particular solid phase, it is easy to purify the compounds here because we are using the solid support. So where the products are attached on the solid support, and that compound will be separated upon simple washings, right? When you give simple washings, you will get the products. So very simple purification is done. But in the solution phase, right? So the purification is difficult. Purification is difficult because if any impurities are there, right? If any impurities are attained in the reaction, so it is very difficult to separate that impurities, right? So to separate that impurities, you need to means you need to keep that column chromatography here, right? So by column chromatography, yeah, that thin layer chromatography, you have to separate that impurities here. Okay, so it's what is that? Some difficult methods are applied in the solution phase. Okay, and automation is difficult. right? So automation is easy in the solid phase. Automation means the operation, right? The operation is very easy in the solid support or the in the solid phase synthesis, right? Automation means the performance, like operation. Okay, very easy. And in the solution phase, the automation is difficult. Okay, so to monitor the chemical reaction, it is very difficult because where you need to maintain the temperature, and you need to add some solvents, and some solvents effect will be involved. Okay, and the temperature, some changes will be there, right? So all these are the difficulties you can face during this the reaction in the solution phase. But in the solid support reaction, no such difficulties are raised here. Okay, and only few, okay, only few suitable reactions are there in the solid support. Like as I told you, only the few reactions are suitable in the solid support here, like your peptides chemistry, and some heterocyclic compound synthesis, and right, and some organic synthesis here. Only few reactions, not all. So, and most probably the peptide chemistry is suitable for this solid support synthesis. So only few suitable reactions, right? Not all reactions are convenient in the solid support synthesis. And when you in the solution phase, okay, in the solution phase, every reaction you can perform in the solution phase, right? Including peptide synthesis, heterocyclic synthesis, organic synthesis, and whatever the reaction is there, right? So natural product synthesis, all the reactions are suitable in the solution phase, right? Okay. And generally the solid support reactions, it is expansive, right? So in the cost wise, the solid supports reactions are expansive because to perform these solid support reactions, right, or the combinatorial synthesis or the combinatorial method, so you need to use some expansive operators here, expansive instruments, right? Expansive instruments are used in the solid support synthesis here. And the in solution phase, it is inexpansive, right? It is very inexpensive or very cheap reactions because you can use, right? So we are not using expensive instruments here. We are not using expensive operators in the solution phase. Simply by taking the beaker and test tube or the boiling tube, you can, right, you can keep the reaction. Simple heating and simple instruments or the operators are used here. Only the in the instruments what you use, simple like water bath, right? Or the operators like boiling tube or the RB flask, right? So by using that simple operators, very inexpensive operators, you can perform the reaction, you will get the product. But in the solution phase, solid phase, you need to go through means go by using the expansive instruments here, right? So cost wise, it is expensive, but you will get the large compounds here, right? Only the advantage of this solid support is the instruments which are used in the solid support is expensive, but the compounds which you are getting is more. Okay, so that is a means every reaction is having merits and demerits. Okay, right. And the scale up is, okay, the scale up is more in your solid support, right? So scale up is more, means the product obtained is more in the solid support, and the scale up is less in the solution phase here, right? So scale up is less because means when you keep to get the one compound, you need to keep one reaction. To get the 100 compounds, you need to keep the 100 reactions. So the scale up is less. And in the solid support, the scale up is more. Means scale up means the obtained products here. Okay, so the final products are more here. By keeping one reaction, we are getting more number of compounds like 50 or 100 or 200. That much compound is obtained in the solid support here, right? Yeah, and well documented, and the time will be means well documented reactions are there in the solid support, right? So in the solid support, you can means more references, right? So very less references are available in the solid support because only few suitable reactions are there in the solid support. So you won't get the more references, more articles or the journals on this solid support. Only less references are available. That is a documentation. Documentation in the sense the references or the journals or the articles here are available for the solid support. And in the solution phase reactions, so you will get the more documentation. It is well documented, right? You will get more references for this solution phase reactions. Okay, so these are the differences, and it is very important here. What are the differences of solid support, means solid support synthesis and the solution phase synthesis, right? So you can list out some differences here. Okay, next. Okay, so coming to the technologies involved in the solid support synthesis here. So in the combinatorial synthesis, there are two methods or the two technologies are involved here. One is a parallel synthesis and another is a mixed synthesis here, right? Parallel synthesis and mixed synthesis. So in the parallel synthesis, right? So what is parallel synthesis here? So the single product is obtained in each different reaction vessel, okay, useful for drug optimization. And in the mixed synthesis, you will get a mixture of products here, right? The parallel synthesis. Parallel means the name itself is telling that parallel means parallelly we are getting the same compounds. Okay. For example, means in the parallel synthesis, in both cases we are getting large quantities of compound. Okay. So the quantity wise, we are getting large number of compounds here, but in the parallel synthesis, we are getting same compound here. Okay. For example, in vessel, first vessel, we are getting alanine, for example. In the second vessel also we are getting alanine. In the third vessel also we are getting alanine, right? So same repetition of the product here. Same product obtained in the large quantity here. But in the mixed synthesis, we are getting different products. For example, in one vessel, if you get the alanine, in another vessel, you will get the valine, right? In another vessel, you will get the phenylalanine. So like that means where the different products here. Okay. So the parallel synthesis, right? It is okay, less useful for the drug optimization. Generally, this method, right? So this combinatorial synthesis, right? The combinatorial synthesis method is useful in drug optimization here. What is mean by drug optimization? So the drug optimization, nothing but where the drug synthesis. Okay. So generally, to get the one drug, active drug, to invent a active drug, right? So it takes 15 to 20 years time here. Okay. If you want to synthesize a active drug, right? So you want to release a new drug in the market, it takes 15 to 20 years time here. It is very time taking process, right? Means if you go through the conventional method or the traditional method, it takes 15 to 20 years here. Okay. But because here, what you do in the conventional method, for example, we'll take, okay, for example, here, we'll take the starting material, right? A, and we'll come react with the B, we'll get the C. Okay. And this particular C. Okay. So this particular C is, this is your drug, just you assume that. This is a prodrug. Okay. Prodrug means which is not having the drug properties here before. Okay. So this prodrug. So this drug is further, it undergoes some characterizations here. Some characterization, then it undergoes some clinical trials here. So many phases are there. In the clinical trials, there are 7 phases are there, right? Phase 1 clinical trials, phase 2 clinical trials, phase 3 clinical trials, phase 4 clinical trials. Okay, like that. There are 7 phases are there. Okay. After that, then some authorities will be approve the drug, right? Like FDA. Okay, FDA. Food and Drug Authority here. Okay, so like that, some authorities which approve the drug here. So these are the what is it? Mm, Steps involved in the new drug invention here, right? For example, if this particular drug, right? So this is the pro drug. If it is not satisfying any stage, if it is fails in any stage, again you need to come back and again you start freshly. You start from A to B again, right? Again you to freshly you start. Again you take A and B. Again you C. Means here what you do, you change the reactant. For example, in the first attempt, right? In the first attempt, if you take that benzene, for example, okay. So with benzene, you get some compound here, drug here, some X drug you obtain, okay. But this X drug is not satisfying the some properties. Like what are the properties there? That is the drug properties called ADME property. Okay, ADME property here. ADME property is a drug property. Absorption, distribution, metabolism, and excretion. These are the and toxicity also there. There are five drug properties are there: absorption, distribution, metabolism, excretion, and toxicity. These are the five properties here, right? So you are synthesized drug, means that is suspected. The suspected drug is not satisfying any one of these property. For example, if it is it passes absorption, it is satisfying the distribution, right? It is satisfying the metabolism. These three phases. If it is not satisfying the excretion, for example, then you reject that compound and again you come back and you start the same fresh synthesis. Okay, so like that. So is it Okay, right. So for the drug optimization, this combinatorial synthesis is very useful here. So in this drug optimization, what you get this means what you do here. So the compounds, all the products which are obtained by this particular combinatorial method are the synthesis here. So it is taken up for the screening here, right? So for example, we go with the 1,000 molecules. For example, we are produced the 1,000 molecules by combinatorial synthesis, right? And we'll go with the 1,000 molecules for the screening. Okay. So where we are performing the screening. Okay. So we are going the screening here. Screening means the removal, right? And we applied some properties like ADME properties. Okay. We are applied the ADME property to these molecules here. Out of 1,000, only the 100 molecules are satisfied, right? Only 100 molecules are screened out, and remaining 900 molecules are screened out here, right? 100 is screened in, means these are passed this screening, and the 900 molecules are removed. They are outliers here, right? They are outliers. So we remove the 900 molecules. Only 100 molecules are satisfied this particular property. And by taking this particular 100 molecules, again, we'll go with the secondary screening, right? Secondary screening here. So in this secondary screening, right, only few of molecules, like 10 or 20 molecules are satisfying the that particular properties which are applied. By taking that 10 molecules, again, we'll go with the clinical trials. Okay, preclinical trials and post-clinical trials. All these methods are applied here. So out of 10, only 2 molecules are screened out here. And by taking these 2 molecules, right? So where we'll send these 2 molecules for the approval here. So that particular different authorities, right? IND authority and FDA authority. Okay. So these authorities are okay. Check that particular 2 molecules and they will approve. So out of 2, only 1 molecule will be passed and this will be marketed. This will be uh, means invented as the final drug compound, and it will be marketed here, right? That is a procedure which involves in this drug optimization, other drug synthesis here. Okay, but what well this is very reducing the time here, because we are not synthesizing the molecules by taking the starting material here, right? What we are doing, we are taking the molecules from the synthetic libraries, right? So the molecules which are synthesized by this combinatorial method or the combinatorial synthesis, they will be preserved in the synthetic banks here. Okay, synthetic banks. So synthetic banks. So in these synthetic banks, uh, the molecules, right? All the molecules are available here. So millions of molecules, not the 1,000 or 100 here. So millions of molecules with a variety of functional group, variety of core structure here, variety of what is that? So the rings here, it will be available. Okay. So by taking all the molecules, we go means we will go with the drug optimization, right? So if any molecules are screened out, then by taking that molecule, we'll go further development of the lead optimization, other drug optimization method here. Okay. So that is for that, this combinatorial synthesis is very useful. Okay. So the requirement for this combinatorial synthesis are the solid phase techniques here. Okay. So to perform this combinatorial synthesis or the solid phase synthesis, right? Some requirements are there. So what are the requirements to perform this solid support synthesis or the combinatorial synthesis? So the first requirement is, right? The first very important requirement is a solid support. Okay, insoluble polymer support. We call that is a solid support here, or we call it is a resin bead. Okay, so the first requirement to perform this combinatorial synthesis is a resin bead here. Okay, resin bead. So if biology people are there, they will know the resin bed. Okay. So resin bed. So you know the resin bed means it is a like this kind of structure here. So it is having the some what is that? Okay. So this kind of structure, resin bed here. Okay. Yeah. So it is porous. Okay. You can see the some porous structure here. Okay. So the first requirement is a resin bed. Okay. And the second requirement is a resin bed. First is a resin bed or solid support. Okay. And the second requirement is a linker, right? The linker or the anchor here. So, right. The second requirement is a linker or the anchor. Okay. And the third requirement is right, the suitable conditions. Okay. The suitable conditions here. And the next requirement is, okay, the availability of suitable reactants. Reactant in the sense, the building blocks here. Okay, the building blocks are next requirement here. And the next requirement is the what is it? Right, a covalently method for cleavage of the product here. Right. So on the solid support, by taking the means by taking the solid support, we will perform the reaction here. Then the product will be obtained. Right. So after formation of that product, you need to cleave that particular bond, which is attached with the resin bead or the solid support. Right. So there is a bond formation will be takes place. That is partial bond only. Right. A partial bond will be formed between the resin bead or the solid support and the product. Okay. So after completion of the reaction, you need to cleave that bond. Right. You need to cleave that bond. So the breaking, okay, cleavage reagent is required here. That is the next requirement here. Okay. And yeah, and the final last requirement is a suitable protecting group here. Okay. A suitable protecting group is very important in this particular solid support reaction or the combinatorial synthesis. So why the protecting group is required here? Because here this particular, for example, if you take the amino acid here, right? So you aim to uh, synthesis a polypeptide here, right? So in the polypeptide, generally we use the amino acids. Okay, acidic amino acids are the basic amino acids are the neutral amino acid, whatever, right? So there are 23 amino acids are there. So out of right 23, we have the acidic and basic and neutral amino acids here. Okay, so the amino acids having the two functional group here, right? So you aware of this. This is the general structure of the amino acid here. Okay. So it is having the amino group here and the acid group. Okay. So in the peptide synthesis, the one amino acid is linking with the another amino acid. Okay. And that the linkage will be takes place by amino group or the acid group, because both functional groups are reactive. Acid group as well as your amino group both are reactive here. Okay. So but if both groups are reactive, right, then we don't means we won't get the our required or the desired product here. Okay. So for example, yeah, so where we are getting where we are taking the alanine, okay, or glycine for example, right? So glycine here, so glycine amino acid and the alanine. Okay. So glycine and alanine, right? So by combining these two, we'll get the right? So glycine and alanine here. So this dipeptide is obtained. Okay. So to get this particular glycine and alanine, okay. So the you take this particular glycine, right? So this is the glycine here. Okay, CH COH, right? So this is a glycine. Then alanine here. Okay, CH3 and COOH. So this is alanine, right? So where here this NH2 should be okay. So this NH2 should be reacts with this particular acid group by removal of the water, right? The condensation, the removal of the water will get the glycine and alanine. So this linkage will be formed. Okay, this linkage will be formed. So for example, if okay, so means when this particular okay, so when this particular acid group is combined with this amino group, then you will get the glycine and alanine. For example, if this amino group is reacts with this acid group, then we will get the alanine glycine. We won't get the glycine alanine, but we need glycine alanine dipeptide, right? But where because the reaction of this amino group with this particular acid group, right? So where we are getting this particular alanine and glycine here, not glycine and alanine, we are getting alanine and glycine. So that is different. So to avoid this problem here, to avoid this problem, okay, to avoid this problem here, so you make this particular, right? You make this amino group inactive, right? So you make this amino group inactive. Inactive in the sense you protect here, right? You protect. So where we are, if you protect this amino group temporarily, not permanently, so temporarily you protect this amino group, then it becomes inactive and it won't involve in the reaction. So definitely it will be, right? The aminol will be going to attach with your alanine, right? It won't involve in the reaction. So then you will get your desired or your required product. Otherwise, the different product, you will get the product, but it is not our desired product. You will get a different product here, right? So to avoid that problem, we will protect the one of the end of the amino acid here, and we will react with the another amino acid. Okay, so these are the requirements for this particular combinatorial synthesis here. Okay, then we'll see one by one in detail of these requirements here. So first we'll see the resin bead, right? Resin bead are the solid support. So in the resin bead, so there are so many types are there, right? So many types. I mean, depending on the functional group, depending on the reactants, we use the specific resin beads here. Okay, uh, in this particular resin bead, right? And very commonly used resin bead is a Merrifield resin, right? Very commonly used resin bead and very important, right? And frequently used resin bead is a Merrifield resin. Very, very important in the examination. Every time this question is repeated, resin bead, Merrifield resin is repeated here, right? So just to see this particular Merrifield resin. So Merrifield resin. So Merrifield resin. What is Merrifield resin here? So Merrifield resin is it is a cross linkage of, right? The cross linkage of polystyrene with 1% divinyl benzene. Okay. So it is a cross linkage of polystyrene with 1% divinyl benzene here. Okay. So styrene, what is styrene here? So this is the allyl benzene is the styrene. This is styrene here. Okay. And divinyl benzene. This is divinyl benzene, DVB. Okay. So when this particular so, right? So here two molecules of, right? Two molecules of styrene. So one is attached here, and this one is attached here, right? So like that, the polymeric structure, the polymeric styrene structures are cross-linked with 1% divinyl benzene, right? Divinyl benzene means this one here, vinyl, divinyl benzene. This is the divinyl benzene. Okay, and styrene is this one. Yeah, right. So here the styrene, divinyl benzene. Here is a styrene. So it is going to cross link with this particular benzene here, right? Then we are getting this kind of structure. We are getting this kind of polymeric structure here. Okay, so polymeric structure. So Merrifield resin nothing but it is a cross linkage of the polystyrene with 1% divinyl benzene is a Merrifield resin. Okay, and yeah, and this particular right. So Merrifield resin, it is attached with the the X group here, right? So X group nothing but it is chloromethyl group here. Chloromethyl group. X is nothing but chloromethyl group. So this X group are the chloromethyl group, this one, right? It is acting as a linker, right? It is acting as a linker or the anchor here. Okay. So this is the Merrifield resin structure here. You can see. Yeah. That is the very important and right frequently used, right? Commonly used resin is a Merrifield resin. And how the Merrifield resin is formed, you can see where the by cross linkage of the polystyrene with 1% divinyl benzene. Okay, right. And the next type of solution is right. So this N-ion dimethyl acrylamide, it is acting as a backbone. Okay, and the N-ion bis acrylamyl ethyl diamine, it is acting as a cross linkage. So this particular cross linkage is attached with this particular. Okay, so this cross linkage is attached with this backbone, and it is going to form this polymeric structure, Shepherd's polyimide resin. Shepherd's polyimide resin by combination of these two backbone and cross linker is going to combine and it forms a Shepherd's polyimide, right? Polyimide resin here. So in the Shepherd's polyimide resin, where one end is protected with right BOC, right? BOC is a bow colony, right? So BOC is a BOC. So that is protecting group here. Okay. Yeah. and the deprotection, right? So generally the deprotection, BOC and FMOC, right? BOC and FMOC, these are the amino end protecting groups here. FMOC also protecting group here. BOC and FMOC, these are the protecting groups here. And this particular protecting groups are deprotected by 20% piperidine, right? So it is deprotected with 20% piperidine. So when you, right, so this is your BOC. Okay. So this is, sorry, this is FMOC. This is your FMOC. So this is protecting group here. So when you use this 20% piperidine, right, so this bond cleavage is takes place. Okay. And you will get this particular product, right? So that is another polymeric resin bead here. Next, the next type of resin bead is a tentazyl resin, right? So all these are the different types of resin beads here. Okay, tentazyl resin. So tentazyl resin. So this is also having, right, polymeric structure, but where it is having the polyether linkage. You can see, right? So this ether linkage. Yeah, right. You can see it is having the ether linkages here, right? Polymeric ether linkages. So these are the different types of right. The solid supports are the resin bits here. And the next requirement is linkers. Okay. So linkers are also called as the anchor here. So this linker, it will be attached to the solid support with your building blocks here. Okay, it is attached with the solid support here. And this linker must contains the, right, the reactive functional group. The linker must contains the, linker means it is linkage between the building block and the solid support, right? It is a linkage, right? It is an intermediate compound between the, right? It is a mediator. Simply we call it is a mediator between the building block or the reactant and the solid support here. Okay, and the requirement is the linker must contains the reactive functional group, right? Reactive functional group, right? So you see here, this is the resin bead here, solid support. Okay, and this is your linker where this linker is having the X functional group. Okay, so this is the complete structure of your solid support or the resin bead with the linker. So this resin bead with the linker, it is going to combine or the reacting with your substrate molecule or the building block here, right? Substrate molecule. So this substrate molecule also having the functional group, right? So every substrate molecule is having its own functional group here, right? Yeah. So okay, so it is having some functional group here. Now what is happening here? Where this Y is, right, reacting with this means it is going to attach with your solid support, right? So before going to the reaction, right, before taking the reaction, the building block or the substrate molecule must be attached with your resin bead or the solid support containing the linker, right? So when this X and Y going to react each other, right, each other, then you see here it becomes Z. So why Z here? Because after combination of this X and Y, a different bonding is going to form here, right? The different bond is formed. That's why it is the bonding is changed here. It is Z. Okay. So now what happens here? Your substrate molecule is gets attached with your building block. With the resin bead. Okay. Then the synthesis is carried out, right? So the sequentially, right? The sequentially, the different building blocks are going to attach or the react with your this particular intermediate compound here, right? So where the next amino acid or the next building block is going to attach with here, then next here, then next, so on, right? So then we are getting this polymeric structure, right? Polymeric structure. So after completion of the reaction, right? For example, if you want to stop the reaction here after attachment of these three building blocks here, right? So you can stop the reaction or you can further continue the reaction, right? For example, if you want to stop the reaction here itself, then what you do, just the cleave the bonding between the, right, the product and your resin bead here, right? So for that, some what is that? You can use 20% piperidine or dilute acids like dilute HCl. Okay, so that is a cleavage mineral acids here, uh, right? The mineral acids can be used to cleave that particular bond here. Okay, so after cleavage of this linkage, right? After cleavage of this linkage here, where this bond is going to break down here, right? So here, then you will get this product, right? So this is your final product where this particular, right, the resin bead with the reactive functional group linker is finally it is obtained as unreactive, right? So it involves in the reaction, right? So after completion of the reaction, it won't get any changes here, unreactive. Okay, so where it is reacts with the building block or the substrate molecule partially, right? There is no permanent bond is formed. Only the partial bond is formed here. And after completion of the reaction, when you cleave with the mineral acids, right, the cleavage will be takes place, and finally it is removed as the with its original functional group and original uh, what is that? Its state here. Okay, so this is the method how the the combinatorial synthesis is takes place here, right? So the first step involves where the attachment of your substrate molecule with the resin bead, right? The resin bead is having inbuilt linker with the reactive functional group here, right? So after attachment of the substrate molecule, the your required the required building blocks are going to react with your this particular intermediate compound. And finally, after completion of the reaction, you can stop the reaction by cleaving that linkage with the resin bead here. Okay, so these are the some methods, and you see here the linkers. In the linkers also there are different types are there, right? So for this particular what is that, attachment of the carboxylic acids. Okay, attachment of the carboxylic acid. Usually we use this chloromethyl group, like in the what is that? Yeah, Merrifield region, right? So in the Merrifield region we have the chloromethyl group like this one, CH2Cl. This is chloromethyl group. Okay, so this chloromethyl group, it is your linker. This is your linker. Okay, so this chloromethyl group linker is useful to release the carboxylic acid here, right? So to release the carboxylic acid, this chloromethyl group is okay. Here, MF resin means Merrifield resin. So it is having CH2Cl chloromethyl group here. So when the carboxylic acid means when your building block or the substrate molecule is having the carboxylic acid group, so the suitable resin is a the suitable linker is a chloromethyl group, and the resin is a Merrifield resin here, right? So depending on the functional group at present on the substrate molecule, right? The depending on the functional group present on the substrate molecule, you have to choose the respective linker and resin beads here. Okay. For example, your substrate molecule is having the carboxylic acid group here, right? Carboxylic acid group here. For example, the acid group is there. So the suitable resin bead is the Merrifield resin, and the suitable linker is a chloromethyl link, right? Chloromethyl linker here. Okay. So here you see the reaction, how this particular chloromethyl group is reacting with your carboxylic acid group on your substrate molecule, right? So by removal of the HCl, okay, by removal of the here chlorine from here and hydrogen here, so where you will get the ester linkage, right? The ester bond is formed here, right? And upon mineral acid like hydrogen fluoride, right? So this ester linkage is, sorry, the ester bond is going to cleave. Easily it is cleaved here, right? Easily it is cleaved, and you will get the respective product. Okay, and yeah, next linker is a hydroxymethyl linker. Okay, hydroxymethyl is the linker. So this is also called as the Wang resin. This is also called as a Wang resin, where it is having this particular ether linkage. Okay, and it is having this hydroxymethyl group. In the previous one, it is having chloromethyl group here, and in the Wang resin, it is the reactive, right? The reactive functional group is the hydroxymethyl group. Okay. Yeah. Next, the linkers which release the carboxamide group. Okay, carboxamide group. So the suitable linker is your ring resin, right? So in the ring resin, this particular amino group is a reactive functional group here. So like that, variety of linkers are available to perform this particular reactions here, and the respective cleavage reagents are required. Okay, and the alcohol linkers are there. So these are the different types of linkers and anchors and your resin beads here, right? Okay. Next, we'll see the methods of parallel synthesis. Okay, methods of parallel synthesis. So in the combinatorial synthesis, there are two methods are there, right? So one is the parallel synthesis and second one is the mixed synthesis. Okay, parallel synthesis and mixed synthesis. And in the parallel, so in the parallel synthesis, we will get same kind of product in each reaction vessel. And in the mixed synthesis, different product is obtained in the each reaction vessel. That is a different. Okay, in the parallel synthesis, we will get the same kind of products here. For example, if you have the 10 reactive vessels here, right? 10 reaction vessels are there. So from 10 reaction vessels, you will get the same product from the 10 reaction vessels in the parallel synthesis. But in the mixed synthesis, you will get the 10 different products from each reaction vessel. That is the difference. Okay. Yeah. So first you will see the methods of parallel synthesis. So in the parallel synthesis, also there are different methods are there, right? So in the parallel synthesis, there are different methods are there. So in that parallel synthesis, very important method is a Horton tea bag method, right? Horton tea bag method, HTBP. Very important. It's very important here. The exam point of view, Horton tea bag method is very important. Right? So every year this question is repeated. Hot and tea bag method is very important question here. In the exam point of view, there are it is asked for the 5 marks here, right? In the 5 marks, it is very important. Yeah. So what is hot and tea bag method? HTBP. Okay. So generally, this hot and tea bag method, it is one of the parallel synthetic method here. In the combinatorial synthesis, it is one of the parallel synthetic method. And from this hot and tea bag method, so at a time you will produce the 150 peptides, right? So this method is useful for the peptide synthesis, polypeptide synthesis here. Okay, and at a time you will produce a 150 peptide, right? So this is in a combinatorial method. You will get the 150, right? You can produce the 150 polypeptides at a time here, right? If you follow the conventional method or if you follow the traditional method to get the 150 peptides, you need to keep the 150 reactions here, right? So 150, by keeping the 150 reactions, you will get the 150 peptide products here. That is traditional method. Right? So from this hot and tea bag method, so you will produce the 150 peptides at a time here, right? Means it is the minimum 150 peptides. Maximum above 1 also you can get here. Okay. So more than 150 peptides are obtained in a short period or in a one reaction, right? Yeah. So the hot and tea bag method, the mint of this particular bag method. So you can see where it is having this particular, right? So polypropylene mesh here. Okay. So it is having the right. So it is having polypropylene here, and in this particular polypropylene mesh, right? So there polypropylene brush is there. Okay, and the polypropylene yeah. So here the resin bit, right? The resin bit 100 milligram is sealed in the polypropylene mesh. The polypropylene mesh, it is container, right? So where its measure is given. Okay, so it is how much it is 3 into 4 centimeter diameter, right? So this measurement it is under this. Okay, so this is mesh, and this polypropylene mesh is sealed with, right? Sealed with the resin. So resin bead. So this is divided into chambers kind of right arrangement here, and each chamber, okay, so each chamber is called the right, each chamber is so pot is called the tea bag here. Okay, and this tea bag, okay, this tea bag here, it is fully polyethylene bottles, right? So this tea bag, whatever it vessels here, reaction vessels, it is kept in the right. So right, this is polyethylene bottle, right? So polyethylene bottle, and this is polyethylene bottle. This one, yeah, you see, this polyethylene bottle is acts as a reaction vessel. So polyethylene bottle is containing the polypropylene mesh, and this polypropylene mesh is containing the 100 milligrams of labels here. Chamber, each chamber is labeled. One, these four like okay. So there are so polyethylene is containing so this suppose 100 grams of solid support here, and this is kept in the polyethylene bottle with this right. So this chambers right? So each tea bag is labeled, right? So here these are tea bags, just to assume, right? And each tea bag is labeled. For example, this is one, this is two, this is three, this is four, other five, this is 22. So like that. So each tea bag is labeled here. And this pipped segment is kept in the polyethylene bottle. And this polyethylene bottle is acting as a reaction vessel here, right? Reaction vessel. So now the equipment is ready for the attachment of your amino acids are the building blocks here, right? So now where we are adding the where we are adding the amino acid in this particular reaction vessel, right? So means in the tea bags here, right? So each vessel, right? Each chamber, this kind of right? So it is acting as a tea bag here. We call this is tea bag, and this each tea bag is labeled. Okay, now we are starting the reaction here, where the first amino acid, right? The first amino acid is added in each tea bags here, right? For example, amino acid one, AA1 amino acid one is added here. So all the okay, so all the tea bags are right added by amino acid one here also one, right? Amino acid one. Okay, so all the tea bags are added. Sorry, amino acid one. Okay, now you add right. So amino acid one. Now you add the amino acid two here, right? Now you add amino acid two this one. Then it becomes okay. So this reacid becomes this tea bag becomes AA1, AA2. This is also same. So same amino acid is added in each tea bags here. Here is the combination is AA1 and AA2, right? So one tea bag is containing this peptide linkage, right? For example, if you wish to stop the peptide synthesis here, simply okay, you wash with the mineral acids like hydrogen fluoride or the HCl, whatever. Then the protecting group will be detached here, and the bond between the resin bead and your amino acid other building block is going to cleave, right? So after cleavage takes place, then your amino acid AA1 and AA2, the pure product is obtained here, right? Or if you want to continue further peptide synthesis here, right? So then add another amino acid in each reaction visit, right? In each tea bag, you add the third amino acid, AA3 here. So like that, you go through that addition of the different amino acids until you get your required product here, right? So until, for example, if you want to synthesize the tetrapeptide, right? Tetrapeptide product here. So you have to add up to AA4. Four amino acids you need to add here. Okay. So, and each time you have to, right? Each time you have to deprotect the protecting group here, because when you are adding the amino acid here, AA1, right? So first you protect one end with the protecting group here, right? So one end is protected, another end is means it is free form, right? For example, the amino group is protected here and acid group is free form, right? Then you, right, protected amino acid is added in the tea bags here, right? Now what happens here? So this particular acid group is reacting with, means it is attached with your solid support, right? Now this side is attached with the solid support, and this end, amino end is okay, the amino end is protected, already protected, right? So now what we are doing, we are adding the second amino acid here, AA2, right? So but the AA2 will not be react with this one, because one end is attached with your linker, and another end is protected. So to react with the amino acid 2, you have to deprotect this particular amino group, right? So with what is that? 20% piperidine or the hydrogen fluoride, you can deprotect the amino group. Now the amino group becomes free in form, right? It is in free in form. When you add the amino acid 2, right? And when you are adding this amino acid 2, this is also one end protected. You protect one terminal you have to protect, and one terminal you leave for reacting, right? Now here the group of amino acid 2 is free in form, and the amino group in this particular amino acid 1 is free in form. So both will be combined and it forms a peptide bond. Okay. So if you stop the peptide synthesis here, simply you wash with the mineral acid, then your pure product will be obtained. Or if you want to go further, you add the amino acid 3. Again, you have to deprotect the amino acid 2 terminal here, and you add the amino acid 3. So like that, you have to do this particular procedure here until your desired compound is obtained. Okay. So this is one of the, right. So this method is very cheap method here, right? So this method is very, what is that? Easy method, and it is very inexpensive method, right? It is very inexpensive and easy and very cheap method here, because no expensive instruments are using in this particular method. Only simple, right? Only simple polypropylene sheet and polyethylene bottles are used here, right? And the resin bead, very few amount, means very little amount, like 100 mg resin bead is enough for this reaction, right? So that's why it is very cheap method and very easy method also, right? And the disadvantage of this method is, so it is a manual method. Okay, the hot on tea bag method is a manual method. So generally, if you do the manual method, means you can expect some errors in the manual method here, because the humans are operating this reaction, the humans are performing this reaction, performing this particular method. So commonly, some human errors will be takes place there, right? So some the reaction or the products are not precise here. Okay, so that is a main disadvantage of this method, right? So some human error will be takes place. That is a disadvantage, because it is manual method here. So the quality, right? So the quality will not be the good here, right? Yeah. And the next one is a automated parallel synthesis. Okay. So in the parallel synthesis, we have two types here. Okay. Automated, right? And manual method. So in the manual method, the example is a hot and tea bag method. And in the automated method, we have two types here, right? So in the automated method, we have grid of wells on plastic plate and pin wells grid array. These two are the automated methods. Automated method means no human, right? So what is that? No human being is operating the reaction. It is machinery. It is automated, means it is machinery method, right? So simply just you put the switch, then the reaction will be takes place there, right? No, what is that? The third person is operating the reaction here, right? And somewhat this method is very precise method, and the human errors will be removed here, because we are not operating the reaction. We are not doing the reaction, right? We are doing the reaction with help of the instruments or the machinery here. That's why this is advanced technique. Automated method is a advanced technique here. Okay. So yeah, first we'll see the grid of wells on a plastic plate here, right? So where, yeah. So you can see here this particular right? So this particular sheet, poly propylene sheet is right. So it is having the right. This is plastic sheet. This plastic sheet, it is polypropylene sheet here, right? So it is arrangement. You can see the well kind of arrangement here, right? And this each well is containing the resin beads and the reagent here, right? Each well is containing the resin bead and reagent. Okay, so both will be present in the well here. In the previous autumn means manual method, like hot and tea bag method, right? So where the reagent is added outside here, right? So after the completion reaction, we are adding the reagent. But here, where reagent is right, it is means we are added before the means before going to the reaction here. Okay, right. So and the next one is a pin and well grid arrays. Okay, so here this pin and well grid arrays here. So in this particular right, the rod kind of arrangement is there. Okay, so this rod kind of arrangement is there, and it is attached with the pin, right? So in this particular pin, the bottom head kind of arrangement is there. So means that is called crown, right? So this crown is the solid support. Okay, so this crown are the pin, right? So the pin, it in the end of that pin, it is having the crown here, and it is acting as a solid support. Okay, and below you can see this well, right? So this well is having the reagent, right? So this kind of arrangement is present in that particular instrument here, right? Now what we are doing, we're adding the reagents, sorry, we are adding the building blocks in this each well here, right? Yeah, for example here, right? So some amino acid one reagent, right? So this building block is added in this well here, right? You add here, and what is it? Amino acid one is added in this well. So in all wells, we are adding the different building blocks are the same building blocks here. Okay. Now what you do? Just you dip this. Okay. You dip this crown. Okay. This rod is there now. So just you dip in the well, right? You dip in the well. Then what happens here? This particular amino acid is gets attached with this. Okay. So this amino acid is attached on this. Okay. So this is well here, right? So this well is okay. Okay, right? So this is your solid support. So we are added the amino acid one here. Okay, amino acid one. Now what you do? Just you dip this rod in this well. Then this amino acid one is attached on this resin bead, right? Amino acid is attached on the resin bead. Okay, now what you do? You add the second amino acid in this well. Amino acid two, you add in this well. Again, you dip this rod. Then what happens here? This amino acid 2 is attached with amino acid 1, which is already present on your rod, right? So rod nothing but solid support, pin, right? Pin. Now again you add the amino acid 3 here, right? Again you dip this rod in the well. Then this amino acid 3 is gets attached with this your uh, crown of your pin, right? So like that, you continue this procedure until your desired compound is obtained. Your desired polypeptide is formed. After formation of your required polypeptide, desired polypeptide, simply you wash with the mineral acid. Then the compound is going to detach with your solid support, and the product is obtained in the pure form. Okay. So this is right. So this is the parallel methods. Means in this particular parallel method, we are getting the same products from each reaction visually here. Okay. So this is the parallel synthetic methods here. And next, the mixed synthesis. Okay, so discuss in the next class about this mixed synthesis. Right, so I'm stopping here. So we'll discuss in the next class tomorrow.
Thank you, sir.